Okay, let's go through. I'll at least say something about each one of these questions on the exam. Really, the main thing is you really need to get to a point where you see a rigid body with forces or whatever, and you just immediately go into those 6 steps for rigid body kinetics. So, my biggest concern is people not seeing that yet, and you need to fix that. So I want to talk about that. The first one isn't rigid body kinetics, it's just circular motion. And so we have this object that's moving in a circular path. It asks for the net force on the object. It doesn't say anything about the forces, so there's no way to like actually add up. Like, we don't know if there's a pin joint or a cable or whatever. The only way to do it is to calculate the acceleration and then use Newton's second law. So to calculate the acceleration of P, we're going to use the watermelon equation. And so I think we have all the stuff we need here. Alpha, it has a clockwise angular acceleration of 15. Clockwise means that this is 0, 0, negative 15. The angular velocity is counterclockwise at 5, so 0, 0, 5. And then R, remember the definition of R, goes from the center of the circle or the sphere to the point that you care about. So that is from where the origin of that coordinate system is drawn to that point P. This thing has a radius of 1.5, so that vector is like this. And so it's 1.5, 0, 0. And then it's just, this is in meters, and then it's just plugging it into the equation above, doing the cross products and stuff to get that answer. Let's see. So that would be the angular acceleration is clockwise, so that is going to be 15 times 1.5, so 0, negative 22.5, 0. Plus, then the centripetal acceleration part is negative 37.500. Okay, meters per second squared. And then Newton's second law says F net is equal to the mass times the acceleration. So this is negative 75, negative 45. 0 for Z, and this is in newtons. Any questions about the first one? Okay, now the second one. So the second and third are the ones that are really, well, I mean, circular motion is obviously important, but the second and third, you need to be looking at this and saying like, okay, I'm going through those 6 steps, okay? So the second one is, let me, all right, there's forces. We're trying to calculate accelerations. And so there's just no other way than going through the rigid body kinetic steps. So the first step is there a fixed point? In this case, there is at the right end. And so the moment of inertia is 1/12 times the mass times the length squared. There's no width given, so we're treating that as 0. Plus the parallel axis theorem part. The distance from the center of mass to the fixed point is 1, that's half of the length. And so this is 13.3 repeating kilogram meters squared. And so now we can go to the free body diagram. We have an unknown force vector over at the pin. We have a weight force at the center. The weight is 10 times 9.81, so 98.1. And then we also have a clockwise friction couple. So clockwise is this way, and that couple is 0.5 Newton meters. Any questions about that free body diagram? All right, so our about point is over here. The first force, I'll do R. The row vector is zeros. The force is Rx, Ry. Can you guys not talk while I'm talking, please? The couple, we don't care about any of this stuff. And so this just adds on as a negative 0.5. And then the weight force. So the definition of the row vector is from the about point to where the force is applied. The whole thing has a length of 2. So this is negative 1, 0. The force is 0, negative 98.1. Okay? Any questions about that? Do we need Newton's second law for this one? No. So we'll just go right to the moment equation. So we have negative 0.5 plus 98.1 is equal to 13.3 repeating times alpha, and solve for alpha. And you get about 7.32. Right. And this is in radians per second squared. And so that's the angular acceleration for the bar. That's the answer to part A. And if you want that as a vector, this is only a z component, so you could write this as 0, 0, 7.32. And then for the second part, we're trying to calculate the acceleration at the left end. That's going to be watermelon equation. We just calculated alpha. That's 007.32. Omega needs to be given, and in this case, we're told that it's 0. It's being released from rest. And then the R vector always goes from the center of the circular spherical motion to the point. In this case, the center of the circular motion is the pin. Everything's moving around the pin. And so this R vector is negative 2, 0, 0. And so the acceleration of the point at the left end of the beam is 007.32 crossed with negative 2, 0, 0 plus this stuff, which all becomes 0 because we don't know that angular velocity. I mean, no, because we do know that it's 0. And the acceleration is equal to 0, negative 14.640 for z. Any questions about that? And now here's the one I really wanted to do, this rolling without slipping problem. This is where most of the mistakes were made in this test. So we have a thing rolling down an incline. The angle is 10 degrees with the horizontal. Yeah. There were a couple perfect scores, maybe 3 perfect scores or something. We're going to use a rotated coordinate system like that. You don't have to, I mean, anytime you do a problem using a rotated coordinate system, it's by your choice. You never have to do it to solve the problem, but it makes this problem a lot simpler mathematically. And the way we're going to do this is we're going to go through the 6 steps for rigid body kinetics. And then we're going to use the fact that this is rolling without slipping. So we know that the acceleration, if you use a coordinate system that's aligned like this, is equal to negative r alpha. So, okay, we'll get to this eventually. Any rolling without slipping problem, you need to use that because otherwise there's no way to know, I mean, we have to dictate that about the motion. Okay, is there a fixed point for this? No. And so the about point is the center of mass. And so that's 1/2 times the mass, which I just gave as m, and I just gave the radius as r. So there's what we know about the moment of inertia. By the way, in any problem where, so I said the mass and the radius are not going to affect the answer to this problem. One thing that means, practically speaking, is you could just choose some values for m and r, and you'll get the same answer as any other m and r you choose. So that's always an option available to you, but I'm going to put it in as these, and we'll see where it cancels out in the equations. Okay. And now the free body diagram. There's a weight force down from the center that's equal to mg. I guess I'm going to write it as 9.81 m. And then we have the two contact forces. There's a pushing contact force, N, and a friction force. So now, anytime something's rolling, there's friction going on. And it's static friction. And if there wasn't that friction force, this thing would just slide down the ramp. And we did an example in class where we showed how rolling, the acceleration from rolling relates to the acceleration of something sliding down. And something sliding with no friction always has a bigger acceleration. So that friction force that's holding this point of contact back is always having the effect of slowing this thing down. Well, it makes sense that has to be true. You have a force going the other way. It has to be preventing acceleration. So this force is going this way. And then that's all the loads acting. Anyone have any questions about that? And now I'll go into the table. Well, I'll start with the weight force. Our about point is the center of mass. That's acting at the center of mass, so the rho vector is 0. The force, so this is the one thing that gets ugly when you use a rotated coordinate system. So our coordinate system is like this. Our force vector is like this. This is equal to 9.81 m. And this angle is, so we're going to end up 10 degrees short of making it to that negative y axis. So you can think of this as, I mean, you can use trigonometry and do it a different way, but this is 9.81 times the cosine of 260 degrees, 9.8, I left out the m. And then 9.81 m times the sine of 260 degrees. So that's negative 1.703 m. and negative 9.661 m. So that's the force, negative 1.703 m, negative 9.661 m. Cross product is 0. Then I'll do the normal force. That row vector, so the definition of the row vector is from the about point to the point where the force is applied. So that vector goes from the center of the disk or whatever to where that n is applied. That's a distance of r in the negative y direction. So this is 0, negative r. The force is in the positive y direction, so 0, n. Cross product is 0 because those are parallel. And then the last one is the friction force. That's at the same point as this normal force. So the row vector has to be the same. F is in the positive x direction. And so the cross product is RFF. Any questions about those? Do we need Newton's second law for this one? Yeah, there's no fixed point. So Newton's second law says negative 1.703 m, negative 9.661 m, plus 0n plus FF0 is equal to the mass times the acceleration, and the acceleration is only going to be along the x-axis, so a0. The useful equation that we get out of this is just going to end up being the x one. We don't care about that n for anything. So I'll write this as FF minus MA is equal to 1.703 m. That's our first equation. Any questions about Newton's second law? And then the moment equation says RFF is equal to the moment of inertia, 1/2 mr squared, times the angular acceleration. And so I'll write this as RFF minus 1/2 mr squared alpha is equal to 0. And that's our second equation. Can you solve this? Well, this can get a little tricky when you have constants floating around and variables floating around. You have to be clear on what are your variables and what are your constants. Our variables are FF, A, and alpha. So this is two equations for three variables. FF, A, and alpha. So we can't solve it yet. But we do know that we have to use the equation for rolling without slipping. And the equation for rolling without slipping says the acceleration vector is equal to A0, and that's equal to negative R alpha 0. And so I can write the third equation from this as A, well, I'll just leave it in the form it's in. So A is equal to negative R alpha. I guess we're trying to calculate A. So I'm going to substitute, so I'm going to rearrange this and write this as alpha is equal to negative A over R. But that's our third equation. And now it's just a matter of solving these three equations. If I go, so if I go equation star, and let me go negative R times equation star plus equation 2 star. We get an equation out of these. So then we have a negative RFF and a positive RFF, and those cancel. And we have a positive MRA. And a negative 1/2 mR squared alpha. And then all these are equal to negative 1.703 mR. And now I can plug equation 3 star into this. And so we have MRA minus 1/2. Also, we have that negative there, so this is plus 1/2 MRA is equal to negative 1.703 mR. You can see here where the M's and R's cancel. Everything has an M, everything has an R. And we get that 3A over 2 is equal to negative 1.703. So A is about negative 1.14 meters per second squared. And now that you have that variable value, if you plug that back into the vector, you get that the acceleration vector is negative 1.140. Or in other words, it's in the negative x direction, so this way at 1.14. Any questions about that? Okay. Does anybody, one thing I wanted to say about this. So remember that the policy is your last exam can replace one of your earlier 3 exams. So if you have a bad exam, it doesn't even have to show up in your grade. But definitely take this as, if you did well on this, everything's on track. If you struggled with these rigid body kinetics problems, especially, it's probably worth coming to office hours or sending me an email and talking about how to make sense out of that stuff. Something just isn't clicking yet. Sometimes whatever, why things didn't work and you know what you have to do to fix them, and that's fine. But if you want to talk about it, I'm happy to talk about it. Yep.
So final test, we will do it in 15 minutes, right?
What?
So we're gonna do the final test in 15
No, I'll give you 2 hours for that.
hours.
Yeah.
And can you estimate how many questions in that test?
I can't really because it depends on the kind of questions. I mean, I guess I can estimate. Yeah. It'll be between 4 and 6 questions probably. Yeah. Yep.
I know this has nothing to do, maybe it has, maybe it doesn't, but I know that for the most part, the ones in charge of our grades are us. Uh, Based on these results for this second exam, are you disappointed about some people?
I mean, I think everyone should just take it as like as an indicator of where you are. You know, I mean, obviously for you particularly, like you had a horrible few weeks leading up to it. I mean, we should, you know what I mean? Like, you shouldn't feel. I mean, it makes sense why it didn't go as well as the first exam, and I know we can fix that. So I mean, if I'm not concerned in that way, really. I think everyone should just take it as like an indicator of like where you are and what you need to do to get to where you want to be, you know. Any other questions? Okay. Does anybody have any homework questions you would like me to go over?
Question 8.
Okay. We're not even doing 9 this year. That problem needs some major reworking.
You appreciate it? No, it doesn't look like fun.
No. And you have to do all that stuff with figuring out the angular velocities first. And then it's a little hard to tell what I'm assuming is parallel and what I'm assuming is perpendicular. So. All right, so let's name these things. I'll call this one body 1, this one body 2, and I'll call these joints A, B, and C. And so, like with all the linkage problems, we're just going to start by doing the rigid body analysis. There's the weight force acting at the center. The mass is 20 kilograms, so this is 196.2. That 500 Newton force, you have to treat it as acting on either one member or the other member. In statics, when we had, I mean, because things got more complicated in statics with this sort of thing, but remember I always said, I'm going to always assume that that's applied to the lower number member at the joint, the lowest numbered member at the joint. So using that rule, I'm going to say that this is part of member 1. But if you put that force on both of those two members, you're going to double count it and your answers will be wrong. And then there's the contact force between the two members. I'll call this the force on 1 by 2. And then last, oh man, I got so excited again that I skipped the first 2 steps. We'll come back to those. I just look forward to the free body diagram so much. So we have this force RA here. So that's the free body diagram. I always say before you do that, is there a fixed point for this member? Yes, it's at A. And so that's where our about point needs to be. And so this is 1/12 times the mass times the length squared. And then since our about point is not the center of mass, we have to use the parallel axis theorem. So 20 times 0.75 squared. And that's 15. That's nice and clean. And so now I'll go to the table. I'll start with RA. That's at the about point. So rho vector is 0. The force vector is RAX, RAY. Cross product is 0. Then the weight force. The rho vector is the vector from the about point to the force. So that is going to be 0.75 times cosine and sine of 40 degrees. Yep. So that's 0.575 and 0.482. And the weight force is 0, negative 196.2. And you get negative 112.723. Next, I'll do that 500 Newton force. It has the same rho vector. The force is 0, negative 500.
Wouldn't it be easier to combine the 500 and mg into a single point force?
Yes, but I didn't do that. And the cross product is negative 287.267. And then the last one is that force vector F12, same rho vector. The force is F12x, F12y. Cross product is 0.575 F12y minus 0.482 F12x. Any questions about that table? Do we need Newton's second law for this one? No. So the moment equation says negative 112.723 minus 287.267. I'll rearrange these two. Minus 0.482 F12X plus 0.575 F12Y is equal to 15 times alpha 1. So that says negative 0.482 F12X plus 0.575 F12Y minus 15 alpha 1 is equal to 399.99. And that's the equation star. We have 3 variables in this equation, so we can't do anything yet. And I've pointed this out a couple times. I guess I'll just keep pointing it out. If you look at the table to count your variables, it'll look like you have 1, 2, 3, 4, 5 variables. But notice that those RA components don't show up in the equations, so they're not a concern to us right now. Later, if we wanted to calculate those, after we're done with everything, we could go back and use this free body diagram and use Newton's second law to calculate those. But skip it for now. Yes?
It would, we could still make enough equations to find those out all at once, though, right?
Yeah. We could. It's just you usually don't need them. Most often you don't need them. So there's no reason to just, to me, there's no reason to just put it in what you always do, you know. But the way you would always go back afterwards to do it is go back and use Newton's second law on that body. All right, so we got one equation, 3 variables. Now we'll do member 2. Does member 2 have a fixed point?
No.
No. So our about point is going to be the center of mass. And so this is just 1/12 times 20 times 1.5 squared. And that's 3.75. Free body diagram. We have the weight force here of 196.2. Here we have the force on 2 by 1. Well, we've already named force on 1 by 2, so let's write this as negative F12 instead, so we don't increase the number of variables. What about that 500 Newton force? That doesn't go here. We've already put that in. You would get the exact same answers for everything if you had not put it on member 1 and you do put it on member 2. That works perfectly fine, but we've already used it, so we don't use it again. And then finally, what about at C? That's a pin and slot joint. So the only force is perpendicular to that slot. I'll draw it upwards, although you wouldn't get anything wrong by drawing it downwards. You just end up with the variable having a negative value. So this is RC. Any questions about that? All right, so I'll start with the weight force. The row vector is 0. Force vector is negative 196.2 in y. Cross product is 0. Then negative F12, row vector is 0. The force is negative F12x, negative F12y. Cross is 0. And then finally RC. A row vector is the vector from the about point to where the force is applied. So you can think of that as a distance of 0.75 times cosine and sine of negative 40.
Just the flip values of the other one. Well,
Sort of one flipped and one not flipped.
Force vector for RC would be 0 and RC, but
The force vector, yeah, 0 for x is, yep, that's right. Oh, dang it. Come on. Oh. Here we go. Okay. So 0.575 negative 0.482. And the force vector is 0 RC. And the cross product is 0.575 RC. Do we need Newton's second law for this one? Yeah. So 0, negative 196.2 plus negative F12x, negative F12y plus 0 RC is equal to 20 times A2x, A2y. And so we have a second equation that says negative F12x minus 20A2x is equal to 0. A third equation that says negative F12y plus RC minus 20A2y is equal to 196.2. And then a fourth equation that says 0.575 RC. Well, this is the moment equation, is equal to 3.75 alpha 2. And so we have this equation that says 0.575 RC minus 3.75 alpha 2 is equal to 0. Okay, I will, I'll extend when this is due through Wednesday, and we'll finish it on Wednesday. Okay? That's all.